Assalamualaikum warahmatullahi wabarakatuh. Okay, today we start our chapter 1, properties of fluid. Okay, so properties of fluid. Okay, properties of fluid. Okay, so learning outcome. So at the end of this chapter, students should be able to define the basic properties of fluid mechanics, understand and analyze the fluid flow problem. Okay, list out and apply fluid basic equations. So actually fluid mechanics is concerned with the static and dynamics of fluid, both liquids and gases. Okay, mechanics is the oldest physical science that deals with both stationary and moving bodies under the influence of forces. The branch of mechanics that deals with bodies at rest is called statics, while the branch that deals with bodies on motion is called dynamics. Okay, fluid mechanics is defined as the science that deals with the behavior of fluids at rest, fluid static, or in motion, fluid dynamics, and the interaction of fluids with solids or other fluids at the boundaries. Figure 1 illustrates a solid block resting on a rigid plane and stressed by its own weight. So the solid sets into a static deflection, shown a highly exaggerated dashed line. So this is the dashed line here, resisting shear without flow. So this is the static deflection of this block. Okay, the liquid and gases. This is the liquid and this is the gases. Okay, the liquid and gas at rest in figure 2 require the supporting walls. So they require the supporting wall here. Okay, to eliminate shear stress. The liquid retains its volume and forms a free surface in the container. If the walls are removed, shear develops in the liquids and a big splash results. If the container is tilted, shear again develops waveform and the free surface seeks a horizontal configuration, pouring out over the lip if necessary. Okay, so the fluid engineering applications as list here. So we can use for breathing is using the fluid engineering applications, blood flow, swimming, pumps, fan, turbines, airplanes, and others. So this is the application of fluid mechanics. Okay, in fluid mechanics we use international system units, which is called, the quantities is more on mass, distance, time, force, and temperature. So the units for the mass is kg, kilogram, distance is for meter, m, time is for second, s, and force is for the Newton, n. And temperature is using the degree of Celsius or Kelvin. So as a unit is written in small caps, example is kilogram, kg, meter, m, and second, s. If the unit is named after someone, the unit starts with a capital letter, especially for the watt, W, Pascal, P, and Newton, N. So and the liter using the L. Okay, and exception is for the unit of liter L. Okay, density for is the density using the symbol of P here, or in Malay is called ketumpatan. So density is equal to M mass divided by the volume here. So the unit is kg per meter cube. So density is highly variable in gases and increases linearly proportionally to the pressure level. Okay, density in liquids is nearly constant. We use the density of water, about the 1000 kg per meter cube. Okay, increase only 1% if the pressure is increased by a factor of 220. Thus, most liquid flows are treated analytically as nearly incompressible. Okay, compare using this density of water 1000 kg per meter cube. So the density of mercury is, okay, 30,580 kg per meter cube, and hydrogen, density of hydrogen is 0.0838 kg per meter cube. Okay, at the same temperature and at the same 1 atmosphere. Okay, the density of liquids and solids depends more strongly on temperature than it does on pressure. Okay, at 1 atmosphere, for example, density of water change from 998 to 975 at 20 degrees of Celsius to 75 degrees of Celsius, a change of 2.3%, which can still be neglected in many engineering analysis. So we use this table for the difference of temperature and the difference of the density. Okay. First, we look at the example 1.2 here. Calculate the gasoline density at 20 degrees of Celsius. The mass and volume are 60 kg and 0.5 meter cube respectively. So we use these equations. Density is equal to mass over by volume here. So we just put all the value here. 60 divided by 0.5. So we get the density of gasoline 120 kg per meter cube. Okay. So look at the back here. This is using the specific gravity of mercury. So we know that the density, okay, and the specific gravity is Sg is equal to density of mercury divided by density of water. So we get the density of mercury and the Sg times by 1000. So we get the density of mercury. Okay, so this is specific gravity or relative density, the equations. Okay, we use this equation for the question example 1.1. Okay, so the specific gravity is the density of a substance is given relative to the density of well-known substance. So we use this one. Sg is equal to density of density of liquid divided by density of water. Okay. So relative density of gas is the ratio of the gas density to the density of hydrogen or air at certain pressure and temperature. Okay, relative density is dimensionless, so there's no unit. Okay, so example 1.3, calculate the specific gravity or relative density for engine oil when the density oil is 880. B, seawater when the density of seawater is 1025. And mercury with the density of mercury is 13570. Okay, so we get the Sg oil. So just put all the value here. And so you get the 0.88. Okay, density of oil divided by density of water. Okay, so on of the seawater. So density of the seawater divided by the water, density of water. So we get 1.025. And the Sg of the mercury. So we put all this density of mercury divided by the density of water. So we get the 13.57. Okay, so this shows that mercury and seawater are denser than water. Okay, this is oil. So there is seawater and this is the mercury. Okay, so this shows that mercury and seawater are denser than water. Okay, the specific weight. So using this symbol of this one. So in Malay it's called berat tentu. So specific weight is the weight per unit volume of fluid at certain temperature and pressure. So we use this equations. Okay, specific weight is equal to density times by G in units Newton per meter cube. So where G is gravity accelerations, unit of specific weight is Newton per meter cube. So specific weight of water is 9.81. Okay, we look at the specific volume or isi padu tentu. Specific volume is equal to V over M. Also is equal to 1 over density. Volume divided by mass or using 1 divided by density. Okay, so when the volume is 12 meter cube, mass 3 kg. So we get the density 0.25 kg per meter cube. So we get the specific volume is 1/P. So we get 4 meter cube per kg. Okay. Or you use this one. So you can get this one. Okay. So example 1.4, find specific weight, density, specific weight and relative density of a liquid with volume 0.5 meter cube and weight 55 kilonewton. Okay. So we get the specific weight is equal to rho g, or you can use the m/v times by g. So we get the or W over volume. Okay, so we get the value here, 8461.5 Newton per meter cube. So density, you get the density is equal to specific weight over G. So you get from this one specific weight, so the G here, so you get the value here. And the specific volume, V over 1/P here, so we get 1.1564 times by 10 power of -3 meter cube per kg. And relative density SG is liquid, so we get this part. So this is the familiar for your test one, like this one. So you must find the specific weight, density, specific weight and relative density of a liquid with volume of and the weight here. Okay, properties of fluid. The compressibility refers to the change in volume, okay, that is subjected to a change in pressure on it. Okay. So actually, the usual quantity used to measure the phenomenon is the bulk modulus of elasticity, or simply bulk modulus E. So we use this one. Okay. So bulk modulus, or E, is modulus Foucault. So we use this equation. Okay, dP over dP over dP over dP per P is called pressure change needed for changing the volume, and this is initial volume. This is volume change, and it shows the pressure increment with volume reduction. E hardest to compress. Okay, this is viscosity, or in kelikatan. So it's a properties that represent the internal resistance of fluid to motion or the fluidity, and that property is the viscosity. The force a flowing fluid exerts on the body in the flow direction is called the drag force, and the magnitude of this force depends in part on viscosity. Okay, this one is between the air and the water here, so it is called the drag force. Dynamic viscosity defined as shear force per unit area. Viscosity is a measure of the resistance of fluid against shear stress or tensile stress, or simply viscosity is a measure of fluid friction. Okay, so we use these equations, and the unit is poise, or N Newton second per meter squared, kg per meter per second, or poise. So we typically use the water here, air, mercury and paraffin oil. This is the value of all the fluid here using the water, air, mercury, paraffin oil. Okay, this is the dynamic viscosity of some fluid at 1 atmosphere at 20 degrees Celsius. This is the difference of fluid. So this is the dynamic viscosity here. Okay, with the Newtonian fluids for which the rate of reformation is proportional to the shear stress are called Newtonian fluid. Water, air, gasoline and oils, Newtonian fluids. Blood and liquid plastic, non-Newtonian fluids. Okay, this is the example of Newtonian fluid and non-Newtonian fluids. Okay, in one-dimensional shear flow of Newtonian fluid, shear stress can be expressed by the linear relationship here. So this is shear stress. Okay, this is Newtonian fluid. Shear stress is linearly proportional to the rate of shear strain. Satisfy Newton's law of viscosity. The line passes through an origin. shear stress, and Newtonian fluid. Okay, example of water, air, kerosene, and mercury. So the line of blue line here is non-Newtonian fluid, and the red line here is Newtonian fluid, and also the blue line here non-Newtonian fluid. Okay, non-Newtonian fluids: paint, polymer, solvent, mud flow, blood. Okay, real plastic and universal, and so on. So effect of temperature on viscosity. Liquid, the viscosity reduces with increasing temperature. The cohesive force between molecules reduces when temperature increase. Gas, the viscosity increase with increasing temperature. Cohesive force between molecules is negligible. Molecular momentum transfer increase, that is increase the viscosity of gas. Okay, this is the part of the effect of temperature on viscosity. Okay, so we look at the kinematic viscosity. So kinematic viscosity is the ratio of dynamic viscosity to density. So two common units of kinematic viscosity are meter cube per second and Stoke. Okay, so look at the example here. Okay, look at an example here. A rod of diameter 20 mm and length move at a speed of 25 ms. So calculate the dynamic